Okay, welcome. This is the week 9 webinar. So the light is at the end of the tunnel. We only have a few weeks left. And it's probably going to be a little bit shorter than usual because really this week I try to make it a bit light because this is when you should really be spending time on the project. Okay, this is because you've now had all the information you need to be able to handle the project, and it's time to get it done. Okay, doesn't mean you have to finish by the end of the week, but definitely have your plan posted on the discussion on the Project 2 discussion board, and maybe even collect your data. And remember that it's very different than collecting data. It doesn't have to necessarily be a survey. It can be collected data. What it can't be is just rewriting someone else's statistical analysis from some article or someone else's project. So it has to be data where analysis hasn't been done yet. Just let you know that. And today, as always, I'm going to answer any questions if you have them. And then you'll notice from the list, it's all about chi-squared. Okay, so I'm gonna chat a little bit about the chi-square distribution. We've had a lot of distributions in this class. We've had, if you remember, we've had the binomial distribution, the uniform distribution, the normal distribution, the student's t distribution, and now we're going to have the chi-square distribution. And the chi-square distribution has very important uses, and that's why it's important to talk about the chi-square distribution. So there's going to be three different types of hypothesis testing that use this chi-square distribution. And the first one is called goodness of fit, and we'll give you an example, talk about what that is. And the second one is called test for independence, and also give an example and talk about what it is. And the third one is called the test for homogeneity. And that's same idea. Give an example, talk about what it is, and we'll go ahead and get there. I might briefly talk a little about the project just because that is, should be a big focus this week. Again, this is week 9, and 9 is an odd number. So there's no exam this week, which means you should have a little extra time to work on the project because it's a lighter week. So just to note, this thing right here is chi-squared. You might recognize that 2 on the top is usually called squared in mathematics, right? And this is a Greek letter. Okay, and I'm not the one that names this stuff, so don't get mad at me. If you are having trouble, like in a discussion post or on the exam next week, trying to figure out how to make that, show up on whatever, then you can just type in chi-square, and that's fine. CHISQUARE, because this is the symbol we use, and this is how you say it. So that is the plan for this evening's webinar. And are there any questions at all? I'm always happy to answer questions. That could be about the project. It could be about anything else too. Any questions? Okay, no, I don't see any questions in the chat box. So I just want to remind you, anytime you have any questions about anything we're doing, post them in the chat box and I'll do my best to answer them always, because that's what a big part of the webinar is. You can get that Q&A immediate time, and I'll be able to immediately answer your questions. Okay, so let's start out with an example. And that is, I actually looked it up. The funny thing is I used this last time I did it, but it's changed. In California, 40% of residents are Latino. Sometimes you call them Latinx. 34% are white. 16% are Asian or Pacific Islander. And 10% are other races. Okay. And again, I looked that up on Google, no problem. And the question is the distribution of races different for California community college students? Okay. Because one thing we want to have at our college is we want to make sure that we're representing the students. Okay. And it could be in California. It also could be in Tahoe, but it's much harder with the Tahoe thing because a lot of students are online, not even living in Tahoe. So that's why I just choose California. Okay. So that's what we want to figure out. Okay. And I will let you know I made this up. A survey was done. So I should say, suppose a survey was done of 300 California community college students. And 125 were Latina, 92 were white, 33 were Asian or Pacific Islander, and 50 were other races. So what can be concluded at the 5% level of significance? Okay, so notice as soon as you see 5% level of significance, that means we're going to be doing a hypothesis test. Otherwise, you wouldn't even talk about level of significance. Okay, any questions on this? What do you think the survey question would be if I asked one of our Lake Tahoe Community College students? What would I ask them? What would I ask that person? Because it's very important in this class to be able to think about what is a survey question, because that will guide you towards what you need to do. What's the survey question? Maybe put the chat box. Pretty simple question. Any thoughts? So what would the survey question for this particular example be? It said a survey was done. So what was the question of the survey? Any thoughts? I don't see you typing it in. Yeah. What is your race? Okay. And put in the chat box what your race is. Okay. Yeah, it might be Latino. Mine is white. Notice that the answer to the survey question, it's not a number. It's also not a yes or no question. You didn't say yes. You didn't say no. You didn't say 33. Okay. You gave me a word as an answer. And I want to remind you that we have never in this class done any hypothesis tests for surveys at which the survey question, sometimes we call it the variable, is qualitative and not even yes, no. Okay, so this is the first time doing one of those. Any questions on the idea? Okay, so we can't use anything we've done in the past chapters because this survey question is qualitative, not yes, no. Any questions on why this is different? Okay, so I am going to let you know that this is still a hypothesis. So we're going to do a hypothesis test. We're going to have an H naught and H1. And unlike all of the rest of the hypotheses, these are going to be written in words. Okay. Writing it in symbols is really difficult. When I first taught this, I had students writing symbols and it was a disaster. So I realized I better make it words. So we're gonna this one needs to be happening in words, whereas all the rest of them were required to be written in symbols, and I always did in my examples. And for any of you who didn't write it in symbols when you were asked, I took points off. So this one is different. This is going to be words. So let me remind you, or let me tell you how it's going to work. Okay. And we're going to have H naught colon. Okay. So we're going to have H naught colon. And then it's the distribution of races at California community colleges is the same as the distribution of races in California. Okay. So we're looking at California community colleges, not just people all over. We want to say, well, does California community colleges have the same races? Okay, so we're just going to look at California, not necessarily Tahoe, just California community colleges. And I want to remark that I'm highlighting the word distribution. So for some reason, if you can't see the highlight, I'm going to say it this way. The distribution of races at California community colleges is the same as the distribution of races in California. Why do you think I yelled that word? And I've done this before for in the webinars. Because this way, yeah, yeah, supposed to, even more than supposed to, you're required to use it whenever you're going to be doing a this kind of hypothesis test, and this is going to be called goodness of fit when you want to see if the distribution of something you don't know is the same as the distribution of something we do know. Okay. Any guess for H1? I left it blank for a reason. What's the difference between H naught and H1? The hint is I don't have to do too much. Any thoughts? How is it? What should I write for H1? Any idea? And here's a hint. What I'm going to do is I'm going to copy this. I'm going to paste it, but it's not going to be the same. H naught and H1 are never exactly the same. What changes? It's very simple. Any thoughts? Rephrase the wording? Yeah, in particular, we're going to add one word in it. The distribution of races at California Community College is not the same. Isn't that easy? And the great thing about an online class is everything is done on the computer, so you can copy and paste all you want, and it saves a lot of time. Do you agree? So the H1 will be the distribution of races at California community colleges is not the same as the distribution of races in California. Any questions on this idea? Any questions? Okay, so the next step in this is to decide what's the name of the hypothesis test we're going to use. Because if you get the wrong hypothesis test, it'll be a disaster for you. So for this one, when you have a known distribution, so we know California, that's just it was very easy to find on Google, no problem. And we're assuming that we don't know the community college students. So if you have a known distribution and you want to compare it with an unknown distribution, then we're going to use what's called a goodness of fit test. So that's going to be the name of the test. And by the way, on the exams and on your discussion post, you do need to be able to write down what the test you're using is. So that is important. So this is a goodness of fit test. Sometimes it's called a chi-squared goodness of fit test because we're going to be using chi-squared. I'll talk about that in a bit, what the chi-squared is. So it's goodness of fit because we want to say, if we look at the sample, does that fit the distribution of this other population? Any questions on the idea of that? Okay, so then what we're going to do is we're going to make a table. And here's how the table works. Notice that the different races we looked at were Latino, white, Asian Pacific Islander, and other. So in my table for the columns, I'll write Latino, white, Asian, I'll write PI because it's short enough, and then other. And then we're going to have two rows. The first row is O. O stands for the word observed. So it's what we observed in our survey. So if we look at this survey, 125 were Latino. So right here, I'm going to type in the number 125. Any questions on that? We had 92 were white. So I'm going to type in 92 for the whites. We had 33 for the Pacific and Asian and Pacific Islanders. So 33. And then other, that was 50 were other races. Okay, any questions on that? Okay, then comes the letter E. The letter E stands for the word expected. And the idea is what would we expect if we were going to do a survey of 300 community college students and the distribution really is what California distribution is. So that would mean that if 40% of all California community college students were Latino, and you randomly grab 300 students, then any guess on how we find how many we would expect would be Latino of those 300 people? The hint is it's not a trick question. Any thoughts? So how would we just kind of figure out what would we expect to have if community college students had the same racial distribution as all of California? How would we do that? Any guesses? Again, it's not that hard. I don't see you typing it in. Okay. So if 40% are Latino and we ask 300 students, then we just take 40% of 300. And remember, 40% of 300 is 0.4 times 300. And 4 times 3 is 12. And we have 300. So it's going to be 120, it turns out. If you go 0.4 times 300, you get 120. And you can do it in a calculator too. Oops, 120. Any questions on that idea? Okay, we do the same thing for white. 34% are white. And 34% of 300. 34 times 3 is, that's 34 times 3 is 102. Okay, or 34 times 3 is 102, and that's the expected white. And then we do Asian Pacific Islanders, and that's 16% are Asian Pacific Islanders. 16% of 300. 16 times 3 is 48. So 48. The good thing about a percent of something 100, the percent and 100 kind of go away. And it's just that number times whatever the something is. And we had 10% are other races. 10% of 300 is 30. Any questions at all on how I've made this table? Because you're going to be responsible for making a table. Any questions on that? Okay, so we have the observed and the expected. Notice the observed and expected aren't exactly the same, but with statistics, you don't have to have if it's not exactly the same, that doesn't mean you can say they're different. Because there's always, little error that could happen in sampling. But if they're really far away from each other, then you can say they're statistically significant. I thought I'd show you. Let me pop in one more thing. In my interactive statistics, I created a chi-squared visualization. And this is what the chi-square distribution looks like. It turns out there's degrees of freedom. And if you have, for this example, you take how many different answers there could be. In this case, we had 4 different possible answers. Subtract 1, that's 3. And that would be the degrees of freedom for our example. Okay, and you'll notice that there's no negative numbers, which you would expect from the word chi-squared, because if you square a number, you don't get a negative number. All right, here's what I'm not going to do. I'm not even going to pretend that we have time to talk about the mathematics behind it. But if you want to learn, you actually need to go to graduate school in mathematics or mathematical statistics. So we're not doing it, but you can do is you can trust that the calculator will work. And we get this, picture. If the degrees of freedom are really high, it's actually not that far from normal. But typically you don't have that high. More like that. Okay, so that's what the chi-squared looks like. All right, so hopefully you're used to the fact that when you're doing a hypothesis test, you're going to get a test statistic and a p-value. And we can use that p-value to decide whether there is statistically significant evidence or not, or to reject the null hypothesis or fail to reject. So any guess on how I'm going to find that test statistic and p-value? Yeah, I'm going to go to the calculator. So here's the calculator. And here's a hint. We're towards the end of the class. We only have a few more weeks. So what calculator number? I tried to make it really obvious. Yeah, calculator 21. Goodness of fit, because that's the name of the test. So again, identifying the name of the test is essential so that you can use the calculator and actually answer the question. So it says type in the values from the observed and expected sets separated by commas. Okay, then hit calculate and the test statistic chi-squared and the p-value p will be shown. So we have observed and expected. So now I got to get them and I can kind of copy and paste and put in some commas. And let's drop some commas in. And then for the expected, copy and paste that. And put in commas. Any questions so far? Okay, then I hit calculate. Okay, it even shows the shape of the distribution. It looks like that. We have a chi-squared, that's our test statistic, is about 19.21. And our p-value is actually very small. So 19.21 is our test statistic. And the p-value is 0.00025. Any questions on this? Any questions? All right. We've been doing statistics hopefully long enough that you can tell me what the conclusion is going to be. Do we reject the null hypothesis or do we fail to reject the null hypothesis? Another way of saying is there insignificant evidence or is there statistically significant evidence? And hopefully you can answer it. So what do you think? And again, this is just like every other hypothesis test at this point. Yeah, definitely we're going to reject the null hypothesis because look at the p-value. The p-value is 0.00025, and we're using a 5% level of significance. So I'm going to write is less than 0.05 by a lot. Okay. Okay, so that means that we get to reject the null hypothesis. So here is the conclusion. By the way, if you're less than 0.01, you get strong evidence. So we could say there is strong statistically significant evidence to conclude that. So just let you know, for goodness of fit tests, okay, pretty much everything we do, it's either going to be there is strong statistically significant evidence to conclude that, or there's just statistically significant evidence to conclude that, or there is statistically insignificant evidence to conclude that. It's almost all similar, but you got to get it right. And now what you can do is basically just copy and paste H1, because that's what we're concluding. So that was the distribution of races at California community colleges is not the same as the distribution of races in California. Any questions on that idea? Any questions? By the way, do you think that, after looking at the conclusion and what we've done, it would be a good idea to do this again with a bigger sample size? What do you think? Is this a case where you want to do this again with a bigger sample size? Okay. So the answer is no. And the reason we have such a low p-value, we got to reject the null hypothesis. And if you get to reject the null hypothesis, you won. Right? You don't need to fight anything. You don't need to try again. You won. No reason to I got to do it differently now because I'm depressed. No, you're excited. You got what you were hoping to get, which is a small p-value. So there is absolutely no need to do the sample again or do a new sample with a bigger sample size. Okay? You do it bigger. If the p-value would say 0.06, then you would want a bigger sample size because then you lost and you almost won. Do you see that? If the p-value was say 0.84, then you give up. You lost so badly, you're going to say, well, it's not even worth trying again. Does that make sense? Any questions on kind of the idea of looking at the p-value and deciding based on the hypothesis test whether you would want to redo the study with a bigger sample size? Okay. And by the way, when we're talking about chi-square tests, there's no confidence intervals. So you don't have to look at that. Whereas if you're doing like your project where you have two samples and they're quantitative, then there's a confidence interval, and then you can say, well, maybe I want the margin of error smaller. But for these, it's all about the p-value only. There's no confidence intervals at all. Any questions on this? Okay, so let's look at another example. It's going to be very different, kind of. Won't look different until we think about it a while. So does it matter what season a person was born in when it comes to the type of car they drive? Okay, the table below shows the season and the car type. Okay, so for example, I was born in summer, and I have an SUV. So I'm one of these 68 people who answered summer and SUV. That's how you read a table like this. Any questions on the reading that table? Okay. So this is actually very different. Okay. Whereas the last one, notice the last one, we had a known distribution and an unknown distribution, and we want to see if the unknown distribution was the same as a known distribution. Here, we actually have two survey questions. The first survey question is, what season were you born in? And the second survey question was, what kind of car do you drive? And both of those survey questions are qualitative. Does that make sense? Because the word summer is not a number, and SUV is not a number either. Okay, so, and we want to find out if knowledge of one helps you understand the other. Okay, gives you kind of better predictions for the other. Any questions on that? Okay. So to do that, what we're really saying is season born in, or are season born in, and car type, are they independent or are they dependent? Any questions on that? So we're going to use what's called a chi-squared test for independence. Okay, and that's again, when you have two survey questions, they're both qualitative, and you want to see if they're independent or dependent. Hopefully you understand it's very different than the last one in terms of kind of what it's looking at. Okay. So here are the H naught and H1. H naught is the season a person was born in, and the person's car type are independent. And H1 is the season a person was born in, and the person's car type are dependent. Notice I screamed it. What does that mean? If I scream those words, what does it mean? Yeah, you must have those words, independent for H naught and dependent for H1. Okay? If you don't, I take a bunch of points off on your test question or discussion board question. Does that make sense? Okay, because really it's all about independence. Any questions? Okay, so the next thing we're going to do, the good news on this one is it's not like it's not like the chi-squared good as a fit test. There's no observed and expected that we're going to have to calculate. Okay. When I first taught it, when I first taught this class, there was, but that's because the fancy calculators didn't exist yet. And I hadn't coded the calculator, for example. So now you don't even have to worry about it. And I'm not going to go through the math formulas that we used to have to do. So there's actually a lot less math in this class, a whole lot less than when I first taught this class. And that's because the calculator does a lot of the work for us. Okay, and when I say first, I'm talking 30 years ago. So it's, technology ages ago. All right, so what do you think we need to do? What do you think we need to do at this point? Yeah, we need to go to calculator. Will this calculator work that we just used? Yeah, definitely not. This is not what we want. We're not using a good as a fit test. So go back to the calculator menu. And again, we're towards the end of the class. You got to scroll down. And which calculator number? Tried to make it obvious. Yeah, number 22, which is test for independence. And what this does is it allows you to type in a table. I do want to give you a heads up, and that is with the calculator I made, If you have any more than 5 by 10, this calculator won't work. Okay. Okay. If it were, by the way, if it were 6 columns and say 4 rows, you can switch the columns and rows and that would still work, it turns out. That's called the transpose. You don't have to get worried about the word. But I made this, I wanted to make it kind of simple and work for all the problems that I ever give you in this class. But I do let you know that sometimes in the real world you'll have more. And in that case, actually, if you really wanted, you can use the spreadsheet that we use for the project. Click on the chi-squared and then you can do as many as you want because it's a spreadsheet. But for this calculator, this will work for everything we do in our class. But if, say, you get a master's degree and you're working on some master's thesis and you want to use this calculator, it may not work because you might have too many variables, if that makes sense. So I want to let you know, give you a heads up for the future, not for this class. Okay, so now we got to put in our numbers. Okay, so 73, 81, 76, 78. So 73, 81, 76, 78. And the second one, 65, 68, 62, 64. 65, 68, 62, and 64. And the third one, 43, 51. 48, 50. And then we hit calculate. Any questions? Any questions on how I entered it into the calculator? All right, our chi-squared is 0.48. And the p-value was 0.998. All right, what does that tell you? What does that tell you? Any thoughts? Okay, it's a good thought. It's independent, but especially in this class, for hypothesis testing, you never get to say H naught is true. All you can say is you don't know. You cannot conclude that it's dependent. Is that clear? You can't say it's independent. You can only say we can't conclude it's dependent. Is that clear? So failing to reject is not the same thing as accepting H naught. Okay. So here's the conclusion. There is statistically insignificant evidence to make a conclusion that the season a person was born in and the person's car type are dependent. Okay, that's not the same thing as saying we can conclude it's independent. Okay, that actually, if you want to be able to say something like that, then I'm going to say this a lot from now on. You need to take not elementary statistics. You need to go to a university and take advanced statistics. And then you'll learn about those things. but we can only do so much in this class. So for this class, it's either if p-value is big, you just say we know nothing. And this is the fancy way of saying we know nothing. Okay. Do you think it'd be worth it in this case to do a bigger study with a bigger sample size? Okay. Look at our p-value. It's 0.998. That's not even close to 5% or 0.05. This is like not hopeful at all. It would probably be a complete waste of time to do a different study, a bigger study with a bigger sample size. So the answer is no on this one. Really, the only time you want to do another study on with this chi-squared stuff is that the p-value is a little tiny above the level of significance. But if it's a lot above, then don't even think about it. If it's below, then no reason to do a study, you won. Does that make sense? Okay, and I did make up this data, but I wanted to make it realistic because my guess is it has no when you were born, like when your birthday was, has nothing to do with what kind of car you drive. Maybe you think otherwise, but I don't. Okay, and they've done lots of studies about birthday and all kinds of stuff. And there's for adults, there's almost no relationship between birthday and anything. Just let you know that. Okay, any questions at all on this idea? Any questions? Just something I didn't mention on the last example. We were able to say that the distribution is different. Here's what you can't say. You can't say why it's different. You can't say it's because there's a whole lot more whites at the community colleges than you would expect. Or sorry, there's a whole lot fewer whites than you'd expect. You can't say that. Or there's a whole lot more Latinos than you'd expect. So you can't, based on the chi-squared test, you cannot determine what the reason is and which is the race that is way off. Does that make sense? If you want to decide which one is way off, then I can tell you what I just told you with the other example. You need to take advanced statistics. And you do something called Tukey analysis, and I'm just not going to get into that because we can only do so much in this class. So you can't decide, which is off. That doesn't work. Just I'll tell you my favorite example that I ever did with chi-squared good as a fit. It was a Tahoe type example. Any guess? That I did personally? Don't think, John. Okay, you probably wouldn't guess. I was a card counter, and I go to casinos, and this was the old days. Things were different now, but in the old days, the mafia ran the casinos. When they spotted a card counter, they'd bring in a cheater. Okay, and what I did is I would use the chi-squared goodness of fit to detect cheating, and if the p-value is small, then I'd leave that table. Since it was mafia, you don't try to like get them in trouble because they kill you, but you could leave and they let you leave. So that was something I would do, and then I would come back like an hour later. I'd play again until they brought in the next cheater, and then I'd leave when I found out they were cheating. So I used good as a fit to see that the distribution of cards that were dealt did not fit the expected distribution of cards for a deck of cards. And that's something that it's like a cat and mouse game running away from the cheater. So that's what I did. And that's, now they don't have cheaters anymore. It's different. Now they just make sure you can't win. So it's different. So little story. It's a fun little story. And that was my use of test the chi-squared goodness of fit test. All right, let's do another example. And here is the following. Here we go. Do single men and women take the same type of vacation? The table below shows the results of a study, and I do want to just give you an apology. I made these numbers up. This wasn't a true study, but you can imagine doing a study and doing a survey. So, pretend that, a whole bunch of people were asked, and the survey question is, the last time you went on vacation, was it international? Was it out of the state? Or was it more local? Okay. And they also asked for gender, and I'm keeping it as male and female only. Just nothing against the other types, but I just wanted to make it simple. And we want to see if men take the same type of vacation as women. Any questions on the question? Okay, this turns out to be different than what we've already done. We do not have a known distribution. Is that clear? We don't know men, we don't know women. We just have a survey. We're not deciding if these are independent or not. We want to say is the distribution of travel for men the same or different as the distribution of travel for women. And it's comparing two groups. Okay, it's a little bit like when we did last week comparing two means or two proportions. Because we have two groups, we don't know about either of them. So we do a study for the men, we do a study for the women, and we compare. The difference, though, is a survey question is a qualitative question. It's not yes or no, and it's not a quantitative. It doesn't have a number answer. Okay. Last time I traveled was more local. Okay. Although living in Tahoe out of state, it's like an hour walk and I'm out of my state. But for most people, it's not quite like that. So just let you know that. Any questions on how this is different from the other two examples? Any questions? Okay, so we can't use what we just did. We're going to have to use something different, and that is called a chi-squared test for homogeneity. Have you heard the word homogeneous before? Have you heard that word? It's an English word, not a math word. Yeah, it's kind of an important word. Okay. So if it's homogeneous, it's like the same. If it's heterogeneous, it's different. So we call this a chi-squared test for homogeneity. About different, or is it the same or different? All right, so here's H naught. H naught is the distributions of vacation type are the same for men and women. And H1 is the distributions of vacation type are not the same for men and women. And hopefully you heard how loud I yelled distributions. And notice it's plural because we got a distribution of men, distribution of women, and we're looking at the two of them. There's two of them distributions. We're not comparing like one unknown to a known. It's just two unknown distributions. Do you see how that works? So again, for the exam and for the project, and for the exam and for not project, for the exam and for the discussion post, if you have to do homogeneity, then you have to have that word in there. Any questions on that? Okay. And what the the hardest part, any guess on what the hardest part is for this chapter? And my definition of hard means that people get it wrong a lot. That's my definition. Easy means almost everyone gets it right. The vocab, not necessarily the vocab, actually, not the wording. The hardest part is deciding which test to use. After looking at the question, and the question would be like this: do single men and women take the same type of vacation? And you have to decide, hey, is this a test for homogeneity? Is this a test for independence? Is this a chi-squared test? Or maybe it's one of the other ones that we've already done. And you have to be able to determine which test to use. And if you use the wrong test, the whole thing is going to fall apart. Does that make sense? Wording's not that hard because we have templates here, basically. Just use a template. But if you don't know which test to use, you're screwed. So it's really important to decide on the test to use. Any questions on this? Okay. Again, there's no observed and expected here. Okay. At least let's put it this way. There's no observed and expected for this class. So any guess on what our next step is going to be? Yeah, we go back to the calculator. And will this calculator work? No, does not test for independence. So we're going to go back to the calculator menu. I'm going to scroll down. And what calculator do we use? Yeah, we're going to use 23. Test for homogeneity. By the way, at this point, you should smile. Look at the list. How much left do we have? Yeah, we only got 2 tests left. We're almost done. And just to give you a heads up, next week, we do regression analysis. The week after, we do ANOVA. So it's only 1 test a week after this week. So we're going to do homogeneity because that's our last test for chi-squared. And it says, enter in the observed values for each of the 2 samples, A and B, and hit calculate. And the chi-square test and the p-value be calculated for you. Okay, leave blank the last rows that don't have data values. Okay, and by the way, if you ever have more than this in terms of data values, then you're gonna have to go to the spreadsheet. But that won't happen in our class. But it could happen in your, 5 years from now when you're doing research or something. But for our class, you're never gonna have this more than that. So now we just plug them in. So we have the men, 29, 47, and 33. 29, 47, 33. 29, 47, and 33. We have the women, or the female, 38, 42, 36. 38, 42, 36. Okay, and notice that's it. Okay, leave everything else blank and hit calculate. And we get our chi-squared test statistic and we get our p-value. So the chi-squared test statistic is 1.404. And the p-value is 0.4956. Okay. Typically on the homework, for example, or the exams that are computer graded, you need to go 4 decimals out. It's never bad to go more than they ask, but it is bad to go fewer than they ask. Just let you know for the computer. Okay, and our p-value, what do you think? Big p-value or small p-value? Do we get to reject the null hypothesis or fail to reject? Or is there statistically significant evidence or insignificant? Yeah, we fail to reject. Notice that I didn't even give you a level of significance. And when you're dealing with this kind of stuff, usually what you typically do is you just look at the p-value, and if it's less than 0.05, then, sorry, if it's less than 0.01, you say there's strong statistically significant evidence. If it's between 0.01 and 0.05, you say there is statistically significant evidence. If it's between 0.05 and 0.1, you say there is weak evidence. And if it's greater than 0.05, you say that there's statistically insignificant evidence. That's typically what you do if you're not given a level of significance, is you kind of use those definitions. So here we have there is statistically insignificant evidence. To conclude that, and notice all you have to do is copy and paste H1. The distributions of vacation type are not the same for men and women. Okay, and notice, very important, IN, insignificant evidence. If you leave out that IN, you have completely screwed up, because that means you literally answered exactly the opposite thing that you're supposed to answer. That's the biggest mistake you can ever make in statistics, is to completely do the opposite thing. That make sense? So don't make that mistake. Any questions at all on this test, the chi-square test for independence? Any questions? Okay, let's do one more example. And it says the following. A study was done asking 100 people. Oops, not who. Sorry about that. How many minutes they spent in the shower last time they took a shower. Okay. By the way, how many minutes did you spend in the shower last time you took a shower? Okay. All right. So you spent 25. I spent about 14. Okay. Everyone spends a different amount. Okay. Some people spend 3. Okay. The mean was found to be 16 minutes and the standard deviation was 4 minutes. Okay. The table shows results. Is the distribution normal? Okay. And we have seen in this class a bunch of times where you have to decide whether a distribution is normal. Now, for project 1, how did you decide whether a distribution is normal? Do you remember? Like, for example, could you use the empirical rule? That was in project 1, you had to do that. Do you remember how you did that? I know it's been a while. It happened, though. I don't see you jumping in. What did we do in the first few weeks of class to decide if it was normal? All right, I don't see you jumping in, so let me remind you. We looked at a histogram. Do you remember that? We kind of took a glance at it and said, hey, does that kind of look bell-shaped? Do you remember doing that? Okay. That sounds pretty good, but there's problems with that. One is it's very biased. Okay. Like one person might feel like it looks pretty normal and another might feel like, doesn't look that normal. It Statistics should not be that way. It shouldn't be, it depends on who's looking at it. That's not good statistics. So instead, what you want to do is you want to create a statistical method to determine normality. And I do want to let you know this is kind of the beginning of how to determine normality. It turns out there's much more complicated ways that, as I've mentioned already twice in this class today, in this webinar, you need to have advanced statistics to totally understand the full depth of normality. So we're going to like just do a little piece of it. And that is the following. Okay. So what we're going to do is we're going to look at the data. And maybe I'll do this so we can see it together. Okay. And there were 100 people that were observed. 20 of them spent less than 12 minutes in the shower. 73 of them spent between 12 and 16 minutes. And 7 of them spent more than 16 minutes. Why are these numbers important? Why are the numbers 12 and 16 important? Oh, sorry, that shouldn't be 16. That should be 20. That was my mistake. Why are the numbers 12 and 20 important? Any thoughts? It has to do with the study. You have to look at the study. Here's a hint. So why are the numbers 12 and 20 important if the mean was found to be 16 and the standard deviation was 4? You remember that? It's been a while. Okay. Well, if you look at 16 minutes and 4 minutes, 4 minutes below the mean, which is one standard deviation below the mean, 16 minus 4 is 12. 4 minutes above the mean, 16 plus 4 is 20. So in between 12 and 20 means within one standard deviation. Do you remember that? So we had something called the empirical rule. And that is if the distribution is normal, then 68% should be within one standard deviation. That was the empirical rule. Okay, so 68%, I made this really easy, of 100 is 68. Hope you can do that in your head too. So the expected number of people within one standard deviation of the mean would be 68. Okay, if there's 68% inside, there's 32% outside, and half is on the left, half is on the right, because the normal distribution is symmetric on both sides. So 32%, so 100% minus 68% is 32%, that's the outside. Half of that is 16%. So 16% of 100 is 16. So if it followed a normal distribution, then we should have 16% below, or 16 people below, and 16 people above one standard deviation. Any questions? Any questions on this? All right, what hypothesis test should be used? What type of test? What's the name of the test? The hint is it's one of the 3 we've already done. Yeah, goodness of fit test, because we have the expected, which is a known distribution called the normal distribution, the most important of all distributions. And then we have the observed, we have the showering, and we don't know if people who, time in the shower is normally distributed. I actually have no clue. And I do want to make it, I'll do a confession, is I did make these numbers up, 20, 73, and 7, because, I don't know, I didn't want to survey 100 people, but I can imagine doing it. Any questions on why this is a goodness fit test? Okay, so then I go back to the calculator. Go to the menu, and I go goodness fit. And I put the observers in. The observers were 20, 73, and 7. Make sure there's commas between them. And the expectants were 16, 68, and 16. Any questions? And I hit calculate. And what do you see? Chi-squared is a test statistic, 6.4301. Oh, I forgot to write down H naught is the distribution of shower time is normal. And H1 is the distribution of shower time is not normal. And chi-squared was 6.4301. And the p-value was 0.04015. Okay, notice this is less than 0.05, but it's not less than 0.01. So you can't say there's strong statistically significant evidence, but we can say there is statistically significant evidence. To conclude that, and then you just copy and paste H1. The distribution of shower time is not normal. Any questions? Any questions on this example of goodness of fit? Okay. What I want to do now, what haven't I told you yet? Yeah, secret word. So the secret word is 3. And that's because there's goodness of fit, there is the test for independence, and there's test for homogeneity. So we've had 3 different hypothesis tests in this webinar. Again, I try to pick words that make sense, but you would never guess. So the secret word is 3. And what I want to do now is talk a little about the project. Okay. And hopefully answer some questions. So do you have a project idea already? So yes. Okay. So if you have a project idea, please post it on the project to discussion board so that I can let you know if it works. Okay. By the way, do not use anything this week or beyond. So do not do goodness of fit. Do not do homogeneity. Do not do independence. Do not do regression analysis or ANOVA. None of that stuff is allowed on the project. Okay, this project should be chapter 10. It should be 2 quantitative survey questions. Okay, or 1 survey question with 2 groups. You choose. Okay, it doesn't have to be people. Okay, unlike project 1, but you have to have sample size over 30. 31 is the smallest. And if you've got 2 groups, that would be 31 and 31, for example. If you had 1 group, but you have 2 survey questions, then that's just 31 people answering 2 questions. Just a few things that you do need to include, just because a lot of people don't. One is make sure you interpret the lower bound of the confidence interval and interpret the upper bound of the confidence interval. Okay? Don't just think you've interpreted the confidence interval. Make sure you look at them separately and talk about what the client's decision would be based on each of them. Talk about if you, let's say you're going to use you should look at the 99, 95, and 90. Decide which works better for your client based on the pros and cons. And you should talk about the pros and cons and then choose. And if you decide, say, in a 95%, then you would say, how big a sample size would you need if you wanted the same margin of error, but a 99%? And there's a little bit of math to do, but we've had it in our class. So that's just a note on that sample size stuff. Okay, so that's important and you should include that. I'm kind of mentioning all the things that are the biggest mistakes that I see on projects. And then number one mistake that was made on project 1 was what? That everybody made this mistake. Something I mentioned right after project 1. I don't see you jumping in, so let me tell you, is not doing a draft early enough. Okay, that was the number one mistake. Okay, do a draft early enough so you can send me the draft, like 5 days before or so. You still have weeks to do it, but don't wait till the last day or two. Do it early so you can send me the draft and I can give you all the information on kind of all the, like the top 10 things to improve your grade so that you can get a better grade. Okay, so that was the number one mistake that people made on the project, was not setting the draft. Number 2 mistake, which this is like the worst I've ever seen, is not getting partners. Okay, make sure you have at least one, better is 2, 3 in your group is best. But don't do it by yourself. It's almost impossible to get a passing grade if you do your project alone. Okay, almost every single person who did it alone did not pass. So got D's and F's. Okay, because there's such a big deduction. Get partners. Okay, and again, project 2 discussion board, post that you want a partner if you don't have a partner. So that is absolutely necessary. Okay, do not use AI. I can tell if you do, and boy, am I mean. If you're using AI to write your paper, I am just gonna look at it, and every little tiny detail mistake, I'm gonna zap you on points. Okay, I can tell. So do not just ask AI to write it for you. It'll not go well. That's another biggie. And sadly, people were using AI. Make sure you use the Google spreadsheet, because I see you actually mentioned that. So make sure you use the Google spreadsheet. And again, we're here to help out. I can help, Patrick can help, any of the tutors can help out. But if you don't ask, I can't help. Okay, so those are kind of the biggest mistakes. Okay, any questions at all? Remember, I told you today's going to be a little shorter than usual because we have a little less to do. All right, what I'm going to do is I'm going to stop the recording. And thanks a lot for those who are watching this, at least not live. That's always better live, by the way. So watch it live if you can. But if you can't, you can't. And I'm going to stop the recording.